Hello, this is the solution to the shear and moment diagram on the quiz given by Majors Brule and Richards in Lesson 27. We'll begin with our shear diagram. Noticing that our loads are all in kips, our shear diagram is also going to be in units of kips. Every shear diagram always begins at 0. The first thing that we encounter is the 20 kip load at A pointing down, which is going to cause a negative jump in our shear diagram to a value of negative 20 kips. Now between points A and B there is no load. Therefore, there is no change in shear. So we have a horizontal line, slope of 0, remembering that the slope of the shear curve is equal to the magnitude of the load curve. There is no load between those 2 points, therefore there is no slope. The 28.6 kip load at B causes another jump in our shear diagram, starting at negative 20, increasing 28.6 to a magnitude of 8.6 kips. Again, between B and C there is no applied load, therefore there is no slope. We have a horizontal line, or a line with a slope of 0. The applied moment at C does nothing to our shear diagram, so this horizontal line continues on to point D, maintaining an internal shear force of 8.6 kips. We now reach the 20 kip per foot distributed load. Again, remembering that the slope of the shear curve is equal to the magnitude of the load curve. In this region between D and E, the magnitude of the load curve is constant, therefore the slope of our shear curve is constant. We can then determine the change in shear between 2 points by calculating the area, or the integral, of the load curve. Area under the load curve being 20 kips per foot times 4 feet, or a total of 80 kips. Beginning at 8.6, our load is pointing down, therefore we end up at negative 71.4 kips, with a straight line connecting those 2 points. We now encounter that 131 kip load before we begin to encounter the ramp load. That 131 kip load is going to cause an increase up, again our load pointing us in the direction that we needed to go on our shear diagram, to a magnitude of 59.6 kips. Now we can begin to deal with this triangular ramp load. Again, knowing that the change in shear between 2 points is equal to the area under the load curve. The area under this portion of the load curve, being a triangle, is 1/2 the base of 6 feet times the height of 20 kips per feet, for a total of 60 kips. Now the next question is, how does this shape look? We know it's going to be parabolic since our load curve is linear. If we notice at point F there is no load, therefore the slope of our shear diagram at point F must be 0. At E, however, we have a negative slope. The only way to go from a steep negative slope to a slope of 0 is, of course, with a concave up parabolic curve, which gets us to negative 0.4 kips, or approximately 0. Our shear curve is closed. We must make sure that we have properly labeled our curve lines. Now, in order to develop our moment curve, our moment diagram, we're going to apply very similar relationships that we used between our shear and our load curve. We know we're going to have to use the area of the shear curve in order to find our change in moment between 2 points. So let's go ahead and find the areas now. The area of this first shape, it's a rectangle. Negative 20 kips times 5 feet gives us an area of negative 100 kip feet. This next portion between B and C has an area of 43 kip feet, as does this area between C and D. Positive areas because they are above the axis. Now we approach a potential problem. We need to find the area of this little piece, but how can we do that without knowing this distance x? Well, we can find that distance x one of a number of different ways. First, we can use our understanding that the slope of this line is 20 kips per foot. We have 8.6 kips with a slope of 20 kips per foot. Tells us we need 0.43 feet of distance to drop to 0, which is exactly what happens at that point. Now we have the distance. We can then compute the area of that triangle is 1.85 kip feet. And the area of the triangle in the remaining part of that region is negative 127 kip feet. Now, in this piece between E and F, we have a parabolic spandrel. Noting from our RDC that the equation for the parabolic spandrel is 1/3 base times height, we calculate this area to be 120 kip feet. We're now ready to begin drawing our moment diagram. We start at 0 once again. We have an area under our shear curve of negative 100 kip feet, which means our change between point A and B on our moment diagram is negative 100 kip feet. Now, how do we connect those 2 points? Remembering that the slope of the moment diagram is equal to the magnitude of the shear curve. The magnitude of our shear curve between those 2 points is a constant, therefore our slope must be constant. Now, the next thing we encounter is this area of 43 kip feet. Positive direction, so it brings us to a value of negative 57 kip feet, again connected by a straight line, since the magnitude of the shear between those points is also a straight line. Now, we might be tempted to just continue that straight line on up to D. However, we cannot forget about the applied moment at C. That applied moment being applied in a counterclockwise fashion is going to cause a positive jump in our moment diagram to negative 37 kip feet. Now we can continue along that same slope of the line using the area of 43 kip feet from negative 37. That brings us up to a positive 6. Now we approach this potential snag again where we've calculated that distance. So since the shear curve crosses the 0 axis at that point, we know we're going to have a maximum or a minimum in our moment curve, and in this case it's going to be a maximum. We're going to increase another 1.85 kip feet, or that brings us to a total of 7.85 kip feet, and this is going to be parabolic. Now we're going to reduce by negative 127 kip feet, which gets us to about 119 kip feet. How is this shape going to be? It's going to be parabolic. We know that. The question is, concave up or concave down? Well, noticing that at this point the slope of the moment curve has to equal the magnitude of the shear. Magnitude of the shear is 0, so it's going to be horizontal, and at this point we're going to have a steep negative slope. The only way to connect those two is by something that is concave down. We now reach the last region. We have an area of 120 kip feet, positive value. We're at negative 119 at this particular time, which brings us up to a positive 1. For all practical purposes, that's 0, and we're closed. Applying the same idea for slope, we have 0 slope at this portion, a steep slope at this region, so it's got to be a concave down shape again. This must be a cubic. Since this is parabolic in our shear, the moment function at that region must be cubic. Parabolic in this region because it is a straight line function, and we have straight line functions in the remaining region of our moment curve.